Hello, everyone, and welcome to today's webinar, Introducing Apex 3.0 Software, now with EDS, EBSD, and WDS. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow up with you via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Dr. Shengsheng Mu joined EDAX in 2018 as an applications engineer. Working out of the Pleasanton, California office, he is responsible for providing technical expertise, conducting demos, teaching training courses, and after-sales support. Shengsheng also performs testing and validation for the engineering department and provides support for the marketing team. Prior to EDAX, Shengsheng was lab manager at the Southeastern North Carolina Regional Microanalytical and Imaging Consortium in Fayetteville, North Carolina. Shengsheng graduated from Chengdu University of Technology with a Bachelor of Science in Materials Science and Engineering, and he earned a Master of Science in Materials Science and Engineering from the New Jersey Institute of Technology. Shengsheng completed his PhD in Earth Sciences at Boston University. Now over to Shengsheng.
Thank you for the introduction. Hello, everyone. Good morning, good afternoon, good evening. Welcome to today's webinar. We are releasing Apex 3.0. This is fully integrated EDS, EBSD, and the WDS software suite. 3.0 is our first version of Apex WDS. More features will be implemented in future releases. Since we've added WDS functionalities to Apex software platform, I want to walk you through the WDS detectors we offer and the advantages of our detectors. Our Lambda WDS spectrometer is with new hybrid optics. We offer two models, Lambda Plus and Lambda Super. The WDS can be integrated with EDS and EBSD. The Neptune integrated system is combined EDS and WDS. The Trident system is EDS, EBSD, and WDS. Our Neptune EDS WDS system rapidly determines major, minor, and trace element compositions and give you the most accurate results. So this combined system improves the accuracy of your results, enhances the analysis of complex materials, and removes the need for expert-only tools and training. With the addition of WDS, it can resolve EDS peak overlap, improve the minimum detection limits by up to 10 times, and provide precise quantitative results. This is the Lambda WDS spectrometer mounted on the SEM column. This is our EDS detector. Our Lambda WDS system uses all of the WDS port and most of the standard EDS ports. So they fit on almost all major brand SEMs and the dual beam FIPS. They do not require microscope with a specialized chamber. Those are the highlights of this integrated system. You also have the option to add an EBSD system to the same SEM column to form a Trident integrated system. This enables chemical and structural analysis. So those are the two models we offer. Lambda Plus utilizes polycapillary optics. The energy range is from 150 eV to 10 keV. It has excellent energy resolution for transition elements. The Lambda Super is a higher-end model. It utilizes hybrid optics, a high collection optics plus polycapillary optics. It extends the energy range. On the lower energy side, it goes down to 100 eV, and on the higher energy side, it goes up to 15.8 keV. It has superior low energy sensitivity and resolution. The Lambda Plus have five, both of them have 5 diffractors, and the Lambda Plus has 6 diffractors to choose from, and the Lambda Super has more diffract options, total of 8 diffractors. The Lambda Super has superior resolution for the light elements like 7 eV for beryllium K, and the intensity Lambda Super has better signal intensity than Plus. On the light element side, like 800 counts per second per nanoamp at carbon K. Our lambda spectrometers are using a parallel beam spectrometer design with integrated polycapillary optics or hybrid optics. So this gives you the superior signal intensity and peak to background ratio. Because we have very good signal intensity, so you can utilize the lower beam currents to prevent damage to some delicate samples. This is an EDS peak around 1.7 keV. Based on this EDS spectrum, it is hard to figure out what element is it because we have many peak overlaps in this region. It could be silicon, platinum, hafnium, tungsten, some of them or all of them above. That's because the EDS has insufficient energy resolution to resolve those peak overlaps. But Lambda Plus and Super systems provide up to 15 times better energy resolution than typical EDS systems. So all of these overlapping peaks in EDS can be well resolved in the WDS spectrum. There are many common or classic overlaps in the EDS spectrum for different applications like titanium, vanadium, phosphorus, niobium, and so on. So all of these problems which cannot be answered by EDS alone can be addressed by using WDS, using the lambda WDS spectrometer. This is a comparison between EDS and the WDS. The EDS data collection is parallel, so which means you get all of the peak information simultaneously. It is fast. For WDS, because one spectrometer can only analyze one element at a time, so the WDS collects data sequentially. It's slower than EDS. but WDS has much better energy resolution than EDS. The peak to background ratio WDS is in the range of high to very high. So for the energy range, they cover, both of them roughly cover the same element range. WDS has superior detection limits, very low detection limits, 10 times better than that of EDS. WDS requires higher beam currents, usually 2 to 20 nanoamp. The spectral artifacts in the WDS spectrum is very rare, and there are some spectral artifacts in the EDS spectrum, as we can see from the previous slide. This is the mapping tab of APEX 3.0. This is simultaneous EDS-WDS mapping. So these element maps are captured by different techniques. Like here, the arsenic and iron are collected by the EDS detector, and the sulfur map was collected by the WDS detector. This is the SEM image of the sample I just showed in the previous slide. On the left-hand side, this is iron sulfide, and on the right-hand side, this brighter part, this is the lead sulfide. So if you map with EDS in this, so this lead M map and this sulfur K map, they look almost identical. You just have different colors. So based on the EDS map, it tells you you have lead sulfide on both sides, but this is incorrect because lead M line is heavily overlapped with the sulfur K line. So actually this portion has a lot of contribution from the sulfur K X-rays. So in this case, when we have this kind of peak overlap, EDS gives you incorrect information. So if we look at the spectrum, so this red outline is the EDS spectrum. We see sulfur and lead are heavily overlapped. They cannot be resolved by EDS. But in this cyan color WDS spectrum, so we see sulfur K and the lead M, they are separated out. So in the WDS map of lead M, we see lead sulfide is only on the right-hand side. On the left-hand side, this is actually iron sulfide. So the WDS map resolves the peak overlap, gives us the correct information of the phase distributions. This is another example of resolving peak overlap using WDS. In this EDS spectrum, we see the silicon K and the strontium L are heavily overlapped. So basically, they are sharing the same region of interest for the EDS mapping. So in the EDS maps, we see it tells us strontium is on both sides of the sample, on the left-hand side and on the right-hand side. But the strontium signal from the right-hand side of the sample is actually from the contribution of the silicon K due to the heavy overlap in the EDS spectrum. So in the WDS spectrum, we can see silicon K and strontium L, they are spaced apart. They do not overlap at all. So in the WDS maps, they gave us the correct information. The strontium L is only on the left-hand side, and on the right-hand side, this is silicon K. This slide shows the platinum M, silicon K, and the tungsten M overlaps. Those three energy lines are heavily overlapped, and those are the common elements used in the construction of electronic devices. In this spectrum, the platinum M and silicon K, we see this EDS spectrum is heavily overlapped, but this element energy lines are separated out in the WDS spectrum. And here, this is tungsten and silicon. The EDS has overlap, and the WDS can separate out those peaks. These are maps of the three elements I just mentioned above. So in the EDS maps, due to the heavy peak overlap, they give us the incorrect phase distributions. But in the WDS maps in the bottom, we can see it gives us the correct phase distribution of the three phases. So those overlaps are well separated by WDS. When you analyze the near surface region of a steel sample, you want to reduce the accelerating voltage to reduce the penetration depth of the beam. But at a lower kV, like at 5 kV, you do not have sufficient overvoltage to excite the K lines of those metals. So you have to end up with using the L lines. So in the L line spectrum, EDS spectrum, which is the red outline, we see those transition metal peaks are spaced very closely. But WDS gives us much better resolution to separate those peaks. So in the WDS spectrum, we see these peaks those transition metal peaks are separated out very nicely. This is quant results. This is the quant results of superalloy. This column is EDS results, and this column is combined EDS and WDS quant results. So if we look at platinum, tungsten, radium, we see the discrepancy between those two groups of numbers are big. So that's because, and the WDS results are pretty close to the certified numbers. That's because platinum, tungsten, and radium, they are heavily overlapped in the EDS spectrum. So when you quant with EDS only, it overestimates the platinum and the tungsten and underestimates radium. But with WDS has much better resolution to resolve those overlapping peaks. This gives you the most accurate quant results. So we see the WDS quant results of those three elements are very close to the actual numbers. So WDS numbers are correct. EDS numbers are a bit off. These are boron EDS and WDS maps from an alloy sample. We see the boron EDS map is noisy, but the boron WDS map has very high quality. This is due to WDS has superior peak to background ratio. Now I'm going to highlight some of the WDS features in Apex 3.0. The WDS functionalities are implemented seamlessly with the EDS GUI. Our philosophy is WDS is a detector option in EDS mode, so we enabled this simultaneous WDS button on the ribbon bar of the EDS data collection GUI. Because EDS is fast, so we use EDS most of the time, and then when EDS hits the limits, we use WDS to improve the energy resolution and to improve the peak to background ratio. So when you click on this button, it enables the WDS icons on the ribbon bar. It does simultaneous EDS WDS data collection, so you can do simultaneous spectrum acquisition, line scan, and mapping. And you have the live and review modes for the EDS WDS modes, which means when you collect simultaneous EDS and WDS data, and you can always switch to the review mode to post-process and review the data you already collected. This is very convenient. Okay, I'm using this video to show you. So I click on this WDS mod button, so enables those icons, and this is the line scan tab. Those are WDS collection settings. This is the mapping tab, and you can switch to the review mode to post-process your data while you are collecting new data. In Apex 3.0, the EDS and WDS spectra can be displayed side by side or overlaid. So in this spectrum collection tab, I'm showing you this is a live data collection. So right now, I have EDS and WDS spectrum overlaid. So this red spectrum is EDS, and we see this cyan colors, this line, this is the WDS scan. So they are overlaid in the same spectrum view, and I can click on this split button to split the spectra, have them displayed side by side. So now I have EDS on the left-hand side and the WDS on the right-hand side. And I can switch to the overlay mode, and I can switch to EDS only mode, and this is WDS only mode. So with this design, there is no overlapping windows. This helps you to easily review the two different sets of data. In the mapping tab, we enabled this map selector. So with this, you can display either EDS or WDS maps or both of them in the same view. This same design applies to line scan tab as well. In this multi-map view, so right now I display both of them together. This is the SEM image. Those are EDS maps. These two in the red box, those are the WDS maps. So I can click on the selector to display EDS maps only, and WDS maps only, or both EDS and WDS in the same view. So you can easily interpret your data. We implemented this advanced EDS slide in 3.0 version. So this slide control can precisely control the insertion distance of the EDS slide. You want to do this because WDS requires higher beam current to collect the data. Sometimes at this high beam current, the EDS detector may be saturated. And with this option, you can control the retract of the EDS detector. You can park the EDS detector at a specific location so that enables that both EDS and the WDS data can be collected simultaneously at their optimum count rates. This is WDS Auto Z. It automatically and accurately positions the SEM stage at the optimal focal plane and guarantees the highest intensity. This is Auto WDS feature. So basically, one click from start to finish, the software automatically does EDS spectrum collection to generate WDS scan list, Auto Z, and the WDS spectrum acquisition. EDS and WDS batch collection settings are managed in this one user-friendly batch list. On the top side, those are the EDS entries, so you can set the EDS data collections for each of the entry, and you can highlight the entry to set up the WDS data collection on the bottom. We implemented advanced EDS WDS quantification algorithm in the 3.0 version. The quant table is with per element option, so which means we have those buttons in front of the elements. For each of the element, there is a per element option. You can click on this button to switch between using a WDS standard or EDS standard. To recap, our lambda WDS systems improves the energy resolution. It gives you improved sensitivity, precision, and lower limits of detection. The advantages of our lambda WDS systems are large energy range, covers 0.1 eV to 15.8 keV, and it has high signal intensity due to the parallel beam design and the hybrid high connection optics. It has compact design. It fits on all of the WDS ports and most of the standard EDS ports with almost every SEM. And we have fully integrated EDS, WDS, and EBSD functionalities in one software platform, the Apex 3.0. Now we have time for some questions. So you can submit your questions through this questions panel here. Okay, I see there is a question. What allows to carry out the best quantification with the WDS? This is a very good question. So let me start from the SEM side. So first of all, you have to make sure your SEM has very good beam current stability. So which means I would recommend a field emission SEM, and maybe I do not recommend using tungsten SEM due to the issues of the beam stability, especially at high beam currents. Usually for the tungsten SEM, the beam stability at high currents is typically quite poor. And on the WDS side, you need to make sure you use the correct WDS standards, which means your standards should be as close as possible to the unknowns you want to quantify. So they have to be matrix matched, and their composition should be close enough. And you want to collect the data with sufficient time to make sure you have sufficient counts to do all of the quant calculation. This question is about lithium analysis. Is it possible to analyze lithium? The answer is no. Both WDS and EDS, neither WDS and EDS nor EDS can analyze lithium. So for the WDS, we do not have a diffractor to cover the energy range of lithium. And on the EDS side, let me start from the basic physics. Actually, the lithium K X-ray from LL to K shell is not an allowed transition. So the likelihood of X-ray emission is very low. So we don't have lithium generation in the first place. So basically we have no lithium to analyze. So for example, the lithium metal oxides, so they are one of the primary reasons to be interested in lithium detection, but there is no lithium X-rays have ever been detected from this group of samples. And for the WDS, we do not have the diffractor to cover this range. And actually, the best practice to detect lithium is using our cipher system, and you can get some information from the cipher system on our website. Basically, cipher is the first and only system that quantitatively reveals the distribution of lithium in the SEM. So cipher uses the composition by difference method to determine the lithium content in metallic alloys, compounds, and complex metal oxides down to single-digit weight percentages. So you can get this information from our website or our marketing materials. This question is, can't other lines be used to correctly quantify in the EDS? Yes and no. Yes, when sometimes, usually you have peak overlaps in EDS on the lower energy range, so you have the option to go to higher energy range to get rid of those peak overlaps. For example, you have for the transition metals, you have peak overlaps for the L lines, so you can go to higher kV to excite their K lines, and you have very little peak overlaps at the over that higher energy region. But the problem, sometimes your samples are beam sensitive, so using such high beam current, it may damage your sample. And it gives you a very large penetration depth. So if you want to analyze the near surface region, you have to reduce your beam curve. You have to lower your accelerating voltage. So in this case, you can only use the L line. And so WDS works better in this kind of application. This question is, how long is the scan time for WDS compared to EDS scan? In general, WDS requires longer time because for EDS, you get all of the peak information simultaneously, and for WDS, you can only do one element at a time, and it scans from lower energy to higher energy, so it takes a longer time. That's why we recommend you to use EDS for most of your work. And when EDS hits the limits, like when you have peak overlaps in the EDS spectrum, or you want to achieve higher peak to background ratio, then you switch to WDS. This question is, are there any new features or major bug fixes for EBSD and EDS in Apex 3? We are always fixing bugs. Yes, we have bug fixes for EBSD and EDS in Apex 3.0 and the next release in Apex 3.1. In Apex 3.1, we will implement new EDS and EBSD features. This question is WDS required to separate overlapping EDS peaks? Yes, because EDS has poor energy resolution, those peak overlaps cannot be resolved. And the much better resolution of WDS can resolve those peak overlaps intrinsically. This question is, in the software, are EDS and WDS spectra always collected simultaneously? basically, if you know what elements you want to analyze using WDS, you can run EDS and WDS spectrum collection simultaneously. If you don't know, if you don't have this information, you can do an EDS survey spectrum in the EDS WDS mode first. The EDS spectrum will help you quickly figure out what elements are in the sample and the elements you want to analyze with WDS. And then you can do the WDS spectrum collection with the elements of your choice. This is a very good question. EDS can do peak deconvolution to resolve overlapping peaks. Why do we still need WDS? So if you are mapping or quantifying elements with overlapping peaks, the results will not be accurate because of the addition of counts from the other elements. Yes, you can do peak deconvolution to correct it, but this approach is secondary and results in a higher error. The deconvolution will be particularly difficult if you have a trace element peak overlapping with a major element peak. For WDS, the peak overlaps can be resolved intrinsically, which means there is no overlap in the WDS spectrum. This is the best practice to give you the most accurate results. Yeah, I think I have time for one more question. Okay, on one of the slides, you mentioned your detector utilized lower beam currents to prevent beam damage. Why the beam current can be lower? Okay, this is because basically there are two major reasons. One is the lambda WDS spectrometer uses a parallel beam design, which is a compact design that shortens the X-ray path, so the signal intensity is higher. The other reason is we utilize X-ray optics to improve the collection efficiency, so high beam current is not required to achieve sensitivity. I see there are some questions I haven't answered. I will follow up with you on these questions via email. Thank you everyone for attending this webinar. Bye.